So now let's switch to the following step in our approach to the general fluid mechanics problem. Let's no longer consider static fluids, so steady states, fluids at rest. Let's move to the case of fluids, moving fluids, dynamic of fluids moving. But let's consider two large simplifications. But, I mean, simplifications that match pretty much our cases of interest, because we are considering perfect fluids and we are considering barotropic fluids. Let's see, what is this? What is a perfect fluid? A perfect fluid is a Newtonian fluid, which we know that is defined, the stresses follow this constitutive equation, but with null or negligible viscosity. So the viscosities, these coefficients, lambda and mu, that appeared in the constitutive equation for Newtonian fluids, these are zero. So if these terms are zero, what is the resulting stress state? That one. It's a hydrostatic type stress state. But this P is no longer the hydrostatic pressure. It's just the thermodynamic pressure. But the stress state, since can be expressed as a coefficient times the unit, is a hydrostatic stress state. So this is not hydrostatics, but the stress state is hydrostatic-like. Okay? Okay. Due to that, it can be really proven, and you have that proven in the book, that the divergence of a hydrostatic-like stress state, divergence of sigma, sigma being that, can be written as the gradient of this scalar, which is P. That's a very simple way proven in the book. You can check it. And then the second condition, we have already visited that sometimes, that whenever we compute the term sigma times d, which is minus P times 1 times d is the trace of d. So whenever we see the product sigma times d, we can always, in this case, in this perfect fluids case, replace them by minus the P, the thermodynamic pressure, times the trace of d. If you compute the trace of d, d depends, this is the symmetric gradient of the velocity, right? If you do that, we'll do that many times. Whenever we see trace of d, always, we can replace trace of d by the divergence, of the velocity. Okay? Okay. So this is just because the fluid is perfect. Perfect means no viscosity. Okay? And by the way, water, in most of cases, for us, is perfect fluid. Second, barotropic fluid. We already talked about that. A barotropic fluid is that in which the density is related to pressure in a one-to-one way, independently of the temperature. In a general context, this is not like that. So there is an equation that we call the kinetic state equation, which relates density, pressure, and temperature. But if that dependence can be totally or approximately removed, then from that we obtain that the density depends only on pressure. That's what we have here. So there is a one-to-one relationship of density and pressure. In general, this is an increasing way. The higher is the pressure, as we move right, the higher is density. Okay? And we can also consider such a cavitation, where cases in which the pressure is negative and the density, because cavitation is associated to the presence of air in the water, so the effective density diminishes. Okay? So that's the situation that we have in a barotropic fluid. Of course, this line can be also approximated by an horizontal line. If this line is an horizontal line, what can we say about the fluid? Can you tell me? It's incompressible. Because then the density is always the same, approximately, if it was. So incompressibility is in a specific case of barotropic fluid. By the way, water, again, is no longer perfect. It is not also perfect. It's also approximately, in our situations, in our engineering cases, incompressible. So that's a very interesting case, because our fluid by excellence, water, is barotropic in the sense it's incompressible, and it's approximately at the velocities that we deal with them, with it, is a perfect fluid. So that's a very interesting case. And now we are no longer at rest. We are considering fluids moving, so water at motion. Okay? So what can we say in that situation? Okay, what are the equations of the problem? Well, let's do a review again, just discounting that we've done many times, about the equations that we have in hand. We have the conservation of mass, the continuity equation, that one. Then we have that the momentum, linear momentum balance, but then, as we said before, since the fluid is perfect, we can replace the divergence of sigma by the gradient of P. So that is the version of the Euler's equation for a perfect fluid. Instead of the stresses in general here, we just put here the pressure. Okay? And finally, we have the kinetic state equation, which now is the relation of the density with the pressure. In the most simple case, density is independent of pressure, it's constant, which is the incompressible case. So look, we have here how many equations? We have one equation here, we have three equations here, we have one equation here, so the grand total is just 1 plus 3 plus 1, 5 equations. And how many unknowns? Well, what is the unknown? The density, 1, the velocity here, and the pressure. So we have 1 plus 3 plus 1, 5 unknowns. So that huge problem, that the general case we are not going to, in that case, gets much simpler. It's just a problem in order to be solved that can be solved, the mechanical part of the problem, since barotropic, as we already commented, allows separating the mechanical and the energetic part and the thermal part. Then the mechanical part of the problem, that is what we are interested in. We're interested in density, in velocity, in stresses, that is in pressure. So then mechanical unknowns can be solved by a problem involving 5 equations and 5 unknowns. Okay? Not so easy as the case of hydrostatic, but so far so affordable, let's speak, affordable. Okay, let's see what happens with that. Then, of course, once we have solved that problem, then we can solve the remaining unknowns by the remainder of the problem. For instance, we have the Fourier's law that relate Q with respect to temperature. Then we have the energetic balance that involves that. By the way, again, sigma times D, you know, in that case is minus P times the divergence of P. That's what I said, can be replaced. And then this is the rho r, and this is divergence of Q, can be related by that. And then this caloric state of equations, suddenly we have the remaining unknowns are the internal energy, the heat conduction vector, and the temperature, 5 more equations, 5 more unknowns that can be solved in the 5 more equations. But in fact, most of cases, we are not going to solve that problem. We are not interested in this very much. We are mostly interested in the mechanical part of the problem. Okay, so the point is that, well, anyway, maybe this problem, 5 unknowns, is a partial differential equation. 5 unknowns, 5 equations can be solved by numerical problem, by numerical methods, yes. But, I mean, engineers come from a tradition where they didn't have numerical methods. So there is a long tradition in trying to solve this problem, the mechanical problem, 5 partial differential equations, 5 unknowns, trying to solve that problem by analytical methods. Okay? So let's see what we can do by analytical handling of these equations before or not thinking of using computational approximative methods.